Hello, I'm Olivier Moisin, DriX USV Operation Manager at iXblue. I'm currently in DriX Control Center at iXblue headquarters near Paris. So we've been asked by our client how DriX would perform in complex conditions. In this video, we are going to concentrate on DriX capability not only to navigate in these conditions, but also to record high-quality data with a particular focus on the multi-beam, knowing that multi-beam are often the most impacted sensors in these severe conditions. A few weeks ago, we conducted this bathymetric survey in La Ciotat in France. At that time, we had quite strong wind coming from the southeast, up to 35 knots. As you can see behind me on the oceanographic buoy that was just next to our survey area, this generated a wave with significant height of up to 2.5 meters, with a peak recorded when we were doing the survey at 4.5 meter maximum. As you can imagine, that was quite harsh condition, especially if you're working on a 7.7 meter vessel. But we were able actually to conduct these multi-beam lines. We were working at a depth between 25 and 50 meters. And we did this survey thanks to DriX outstanding seakeeping capabilities. So I suggest we directly check at the data by replaying a file. We'll have the real-time online view of what the data looks like. If I just start replaying the file, there's many information on this screen. This is our navigation software. Though on the right-hand side, you have the navigation display where you can see the DriX and the bathymetric data in a grid. Just below that, we've got an information called the helmsman. On the left-hand side, you've got two curves, the eve and the pitch. And just above that, you have the multi-beam swath. So if we analyze window by window, on the bathymetric swath, what you can see on the navigation display, I'll just increase the exaggeration just to highlight everything. Okay, that's quite interesting because often when you start working in high sea conditions, you will start to have bubbles or motion artifact in your data. What we can see actually, even with an exaggeration 5, is that the data is still perfect. We've got the features that we can see on the bottom, and we've got the full swath of the multi-beam and clean data, no spikes. If we go down to the helmsman, so the helmsman is showing how far left or right is the DriX from its line. We can see that it's actually staying within 1 meter to this line, which is exceptional for the weather condition that we had that day. Then if we look at the eve, the range is about 1.2 meters to minus 1.2 meters. So that's quite important. That's less than the waves, but we will see that due to its design, it's actually lowering the effect of the waves. And the pitch, we have a pitch of plus to minus 5 degrees. It's quite stable. And most of the multi-beam manufacturers are providing a multi-beam system that are able to stabilize in pitch from plus 15 to minus 15 degrees. So we still have really interesting configuration to be able to do our survey. Now if we switch on to our processing software, just to show you the overall results of our survey. Well, if I zoom on the lines, we can still see all the features that I showed you. So there's still no motion artifact on the data. Data looks really nice with all the features on the bottom. If we switch on to the uncertainty, well, we can see that on the coverage between lines, we've got about 10 centimeters to 15 centimeters max between the lines, but that's a maximum. And then finally, if we use the cross line that we surveyed in order to qualify our survey using the cross-check tools, It's going to take seconds to load, but basically you're just showing your swath onto the data. I will switch on to the special order, which is the RHO specifications, and where we can see that the complete swath is way within the special order separation, which has the yellow line on top and on the bottom. And we can see that over the swath, this 95% distribution data we can see in purple, it's actually staying almost constant. With usual multi-beam that are on noisy platform, we tend to have the outer swaths that are increasing with the on the outer beams and getting way closer or past the special order, so that we'll have to actually reduce the swath. In our case, we are actually able to fully use the complete swath of the multi-beam. We need to have a closer look at DriX design that is providing the USV with stability and balance, even in rough seas. This results in a highly hydrodynamic shape comprised of a monohull and a drop keel. This drop keel is going down 2 meters below the surface, and that combination makes the DriX uncapsizable. This piercing wave designs lowers the impact of the waves, as we've seen on the eave measurements in the example behind me. We also have a trimmer that is installed in the keel that will compensate the roll motion of the DriX to maintain it still even when the wave and the wind is pushing. At 2 meters below the surface, the gondola is hosting the payload. It's a reduced noise, bubble-free, anti-cavitation environment, thanks to its shape, but also the material it's made of. And this offers optimum data acquisition conditions. Now let's have a look at the low noise curves recording with DriX. Behind me, you've got an example of noise curve that we recorded with DriX and that we are comparing with other conventional vessels. What we can see on DriX is that the noise is really low. We are about 40 dB when we are not, we are 0 to 4 knots. This 40 dB is more or less the ocean noise, I would say. Now, if we increase the speed, we see that the noise is increasing a little bit. But if we try to compare that to conventional survey vessels, we'll see that the noise is already higher, but as the speed is increasing, the noise is increasing almost exponentially. This low noise on DriX makes data cleaner, but will also allow you to enhance the performance of your acoustic system, whether you're using a USBL system or multi-beam system. We have done some tests with DriX at depths that are greater than the one that we showed today, 100 to 200 meters. And we could see that when conventional surface vessels will start losing the outer beam of their swath as the depth is increasing, we'll see that the DriX is able to maintain its swath, which means that you will have a better coverage in your multi-beam, and so you will gain in production. And that's a really interesting feature. Another key point is the integration of all the sensors within the gondola. We've got the INS really close to the multi-beam and in a tight coupling with the GNSS, which makes a perfect combination. As a hydrographic surveyor, I have done surveys in this hard condition with conventional survey vessels from 25 to 40 meters. And we were definitely not enjoying our time out there. DriX, however, is able to perform this survey and then reduces the standby from your operation. And this can be done from up to 50%. And it will also be done at a lower cost than a big conventional survey vessel. Furthermore, as we saw earlier, DriX is able to record high-quality data with a much lower noise that you would have on any other vessel that you would use. So this increases your production, and it's also decreasing the time for your overall processing. So overall, DriX is a true asset, and taking into account the fact that we are now able to conduct and supervise all of our operation here in the control center makes it even more exciting to use. If you're interested to know more about DriX and about this survey, make sure to go on DriX webpage and download the full survey report. If you've got any questions, you can contact our team and they will reply to any question that you might have. Thank you very much.